First, I would like to thank Christine for inviting me. It's a pleasure to be here. And second, I also want to point out that, Dr. Sweetholm mentioned that there are several comprehensive care centers for pandas and pans. I'm in the Department of Neurology at Columbia University Medical Center in the northern Manhattan, not very far from here, although some of you may think it's too far. Traffic was 2.5 hours to come here at 4 o'clock. However, we are trying to build a comprehensive care center right now that includes pediatric neurologists, pediatric psychiatrists, infectious disease. And so if you're really desperate in need, I highly urge you to contact me, and I'll get you in touch with physicians in my department who are actually treating patients with the disease. So keep that in mind. With that, I'm going to keep this very brief. I'm actually a basic scientist. I'm not a clinician. So we've been interested for a very long time in my lab in trying to understand a little bit about the blood vessels in the brain. Before I start telling you a little bit about that, I just want to make sure that if you haven't read these two books I'm going to show you, you read them, because you'll understand that there's a lot of similarity between autoimmune encephalitis and pandas and pans. So this book, Brain on Fire, was written by Susanna Cahalan. She was a 24-year-old journalist who had a sudden onset of a lot of neurological and psychiatric manifestations. And it turned out that she had actually antibodies that entered the brain and attacked a group of synapses called the glutamatergic synapses. These are basically the ways neurons communicate with one another. And so in this book, she actually describes a lot of the symptomatology and really the struggle that she had to the identification of a disease, which was done at NYU Medical Center. And so I strongly urge you to read that. And then the other book that I recommend is basically Saving Sammy, which you heard from Tim, that this was the book that triggered his interest in the disease. And here, Beth Maloney really gives a very nice description about pandas. And so for a lot of you who are still struggling to understand the disease, this might be a good introduction. So with that in mind, basically the idea that we have, so one of the things that is really intriguing about these diseases is that, as Dr. Sweetholm mentioned, we have a misdirected immune response. We have basically these antibodies that circulate and then they somehow enter the brain. And so in the case of, in the left here, of the autoimmune encephalitis, these antibodies attack a particular group of synapses. And on the right, in pandas and pans, they attack another group of synapses called the dopaminergic synapses. But we were interested in trying to understand how these gain access to the brain. And that's the reason I got interested in the question, because we're interested in the vasculature in the brain. And so in the brain, unlike a lot of other organs, the blood vessels are very different. So if you take a blue dye and you give it to, in this case, an animal, and you allow it to circulate in the blood, that blue dye will rapidly go into the other organs, kidney and liver, but it doesn't enter the brain. And that's because the blood vessels in the brain normally are designed such that they won't allow things to go in the brain. And we know a lot about what regulates this process. I'm not going to go into the detail, but one of the things that they do is they don't allow a lot of the immune cells or antibodies to enter the brain. And so this triggered our interest. Why in these diseases these antibodies have free entry into the brain? What is going on? But I'm going to show you the model that we came up with. And this is based on animal studies. So as I said, I'm a basic scientist and I work on animals. And basically the model that we came up at the very end is actually described here. So it may seem complicated, but we're looking at the immune response that animals develop over stress. And what we find, there are actually two arms of the immune response. The one here are antibodies, And the other one are these immune cells called Th17 cells, or T cells, that you heard in the movie from Dr. Patrick Cleary, who was a collaborator in the study that was published earlier last year. We worked together on this question. And I think the key message from this slide that I want you to think about is the response to strep is very complex. On one side, the body generates these structures called the antibodies, and these basically go and attack the central nervous system. But the question that we had is, how do they get into the brain? And what we were able to show is that indeed multiple, but not single, infections with group A strep trigger in the nose an immune response that leads to the generation of a particular class of the immune cells called Th17 cells. Typically, these cells serve to protect you. However, they can become overreactive, and they have been linked to virtually every single autoimmune disease that we know. In multiple sclerosis, that's the cells that you get that enter the brain and cause the attacks. In a lot of other autoimmune diseases like psoriasis, lupus, you get a lot of these immune cells. And so what we found out is indeed that these immune cells are generated in the nose, and then they sneak into the brain through a route we use every day, the sense of smell. They basically, the nerve cells that are responsible for the sense of smell connect the nose to the brain, and that's what these cells are using to get into the brain. They use these particular nerve cells. And in the brain, once they are in the brain, these do two things. One is that they activate this cell called microglia, which is the innate immune cell in the brain. The second thing that they do is they break down the blood vessels, allowing then the antibodies to enter into the brain. So what does this tell us about potential treatments? Well, the first thing is, are these T cells present in the children with PANDAS? And we were able to show that indeed they are. If you take tonsils from these children and you actually expose the tonsils, the T cells from the tonsils to group A strep, these T cells then become reactive. They think there is strep around. They actually begin to produce a lot of certain molecules that are characteristic for breaking down the blood-brain barrier. And so, but the question is, again, as Dr. Sweeto said today, and also in the movie, that she's been interested and we're interested, is why not all the children develop this? And there are a lot of factors that we're interested in working on. And one is basically that there are a lot of varieties of strep. And one type may be better at doing this than others. And so I urge the physicians here, if you get children with strep, or even the epidemiologist, please send us the strep strains, because we're interested in trying to work in our laboratory to identify what is the subtype of strain of strep that may cause the disease. So it's very common for physicians to do a rapid test and not bother developing a culture. We want those bacteria to understand. The other thing is the genetic risk factors. And you heard from Dr. Frankovitz and Dr. Sweeto that indeed there are genes in your body that may predispose you for this. But I think the one thing that is important that we found out from our study is that the repeated infections are critical. So even though the disease onset is acute, these infections are not a single infections. The child probably has had multiple infections, most of them undiagnosed. But the onset of the disease is acute, and we think that these multiple infections are really critical for maturing immune system to be able to produce the disease. And we think that the presence of both components of the immune system, the antibodies and the T cells, is really critical for the disease. So what does this mean about treatment, potential treatment, particularly in the cases that are very cryptic, that are hard to treat? I think that basically one of the things that our study can tell to the clinicians is that indeed better tests could be developed. One of them is basically this test here. We know these T cells produce certain molecules that break down the blood-brain barrier. And so development of particular tests that could screen potentially the children for the presence of these molecules is really critical. And so we're interested in looking at this in detail in the laboratory. And in addition, for example, if you have relatives who suffer from multiple sclerosis, you know that basically one of the tests that you do is an MRI or CT to look at the barrier disruption in MS. These are active lesions in MS. So perhaps we could develop similar tools, imaging tools, where we could look for changes in blood-brain barrier function in the context of the disease. And then really right now at the very end, we're really thinking about developing perhaps novel immunomodulatory therapies that would not only target the antibodies that you heard, IVIG and plasmapheresis, but perhaps also these other immune cells. Some of these drugs are used for a lot of autoimmune diseases, and so including MS or other autoimmune diseases. And so maybe for the providers, physicians, it's time to kind of open up this other set of tools. And with that, I will close. Thank you.